Okay, so let's continue with looking at linearized elasticity. I'd said we'd start looking at the balance of linear momentum. I did realize that there is one more thing I do want to say with regard to the stresses. And actually, this has something to do with the kinematics as well. And this question is what happens with all the different stress tensors we have defined. Okay. For this purpose, let me go back to our relation for the second Piola-Kirchhoff stress, which we wrote out as a residual stress, which I said we could typically assume, which is often taken to be zero. But let me just for a little bit bring that residual stress back into the game, and let me rewrite this as. Okay, actually, let me write this in the form that we had originally, and then go to a more convenient form. Okay, this is the form we have, and it's an approximation. Now, for brevity, I'm going to write this as S naught. Our residual stress is S naught, and this I'm going to write as C naught contracted with E. Contracted with epsilon. Okay? All right, so this is what we have. Let's look at the other stresses now. We know that the first Piola-Kirchhoff the first Piola-Kirchhoff stress P equals Fs, all right, which is isotropic tensor plus partial of u with respect to x, S, which is now S naught plus C naught contracted with epsilon, right? Okay, and I'm writing equal to signs now, but okay, so we're now in the regime of linearized elasticity. So let's, I'll have to, otherwise I'll have to keep going back and correcting all my equal to signs to be approximations. Let me do that. Okay, this is what we have. Right, now again we can see what happens, right? If the residual stress is non-zero, what we're seeing is that when we write out this expansion, we get terms up to first order, right, in the strains, right, or in the displacement gradient. Okay, so we see that properly this thing, when written out, takes on the form S naught plus partial of u with respect to x, S naught plus C naught contracted with epsilon, right? All right, plus partial of u with respect to x acting on C naught contracted with epsilon. Okay, so we have a certain number of, we have a constant term, two linear terms, and a term that's now quadratic in the displacement gradient. Okay, as before, we say that because this is of order 2, in the displacement gradient, right, we can neglect it. All right. Now you observe that what happens though is that if you have a residual stress, there is another term, right? There is another term that's linear in here. Okay? This is another term that's often missed out in linearized elasticity. The argument that's offered is that for many materials of interest, the tangent, right, is much bigger than the actual stress, right? If you think about metals and other non-soft materials, okay? So in comparison, the third term is much greater than the second term. Okay, so that even if you have a residual stress, if the tangent is not doesn't give you a very soft material, you can afford to neglect that linear term which involves the residual stress. Okay, so if the Euclidean norm of this quantity is much bigger than the Euclidean norm of S naught, okay, one can say further that P is now approximately S naught plus C naught contracted with epsilon. Okay? And furthermore, it's just equal to C naught contracted with epsilon if we say that S naught is small, right? Or if you neglect the residual stress, right? Or if you say there is no residual stress, then you have again the first pure law Kirchhoff stress is pretty much the same as the second pure law Kirchhoff stress. Okay? And this process really goes on, right? If you now consider the Cauchy stress, or let's first look at the Kirchhoff stress, right? Okay, and the Kirchhoff stress tau is F S F transpose. Okay, when we work this out, all right. Now, when you carry this out and we write terms only of 0 and first order in the displacement gradient, we get the following, right? We get S naught plus C contracted with epsilon naught, sorry, C naught contracted with epsilon, plus we get terms of the form right? I think that's all. Okay? Right? Plus of course higher order terms. Right? The squares and the cubic terms. All right? Once again, right? So up to first order, this is S naught plus C naught contracted with epsilon plus partial of u with respect to x S naught plus S naught partial of u with respect to x t, right? Actually, I realized that the second line is not an approximation, that's exact. Okay, the third line is an approximation, right, when we drop the higher order terms. And then, of course, if we furthermore say that the Euclidean norm of C naught is much bigger than the Euclidean norm of S naught. We're left with S naught plus C naught contracted with epsilon, right? And this holds if that Euclidean norm is much bigger than that one. Okay? And then finally, if S naught equals 0, right, if we are neglecting the residual stress, we see once again that tau is all right. Okay. All right. Finally, the Cauchy stress. Okay. The Cauchy stress sigma equals 1 over determinant of F times tau. Okay. Let's assume that we've come as far as reducing tau to being linear in epsilon, right, like the second line of this slide, right? Then we really need to just worry about what happens with determinant of F. Now, determinant of F, right, if you write it out, what you will see is that the it takes on the form, takes on the form 1 plus trace of F, okay, plus higher order terms, okay, plus terms that are of order 2 and 3 in the displacement gradient, right? We know that in general, we know that the determinant of F is actually turns out to be cubic in the displacement gradient, right? So this is the form that it has. Okay. Now, once again, neglecting terms that are of that are of higher order. Okay, one can say that determinant of F equals 1 plus trace of F. Okay, and therefore 1 over determinant of F, okay, equals 1 minus trace of F, okay, up to first order. Okay, and this is just the Taylor series expansion of 1 over 1 plus x. Okay, so if you write 1 over 1 plus x in a Taylor series, you will see that the first order term is 1, the zeroth order term is 1, the first order term is minus x. First order term is minus x, and then there are higher order terms. Okay, so up to first order, 1 over determinant of F can be further approximated as 1 minus trace of F. Okay, but then if we want to maintain just linear terms in our expression for tau, right, if we make the substitution from 1 over determinant of F, what we see is that sigma is approximately 1 minus trace of F times tau, which is C naught contracted with epsilon. Okay? Once again, if we want to maintain just linear terms, okay, so to first order, this too reduces to just C naught contracted with epsilon. Okay? So, what we've seen here is that rigorously, long as we decide to maintain just linear terms, first order terms in the displacement gradient, and of course if we decide to neglect the residual stress, then we do indeed end up with this conclusion that all the stress tensors essentially reduce to the same thing. Okay? However, this development also showed us where we are dropping terms for each one of the stress tensors, right? So if you do want to put back the residual stress, then you know what you need to add back in. And likewise, if you say that the that this elasticity tangent does not have a large Euclidean norm relative to the residual stress, you know how to add back that effect. Okay, so what we are seeing is that if S naught is very, very much less than this, and furthermore, not only that, but we also see that S naught is approximately that, right? Then what we are seeing is that all the stresses are about the same, right, to first order. Okay, so as far as linearized elasticity is concerned, everything is the same. All the stresses essentially collapse to the same thing. Okay.